Hey guys, welcome to Noob Makes Chess with C++ and SFML 2. I'm going to show you what I did this week, and then we'll get to how I made it. So let's compile. And right off the bat, you can see I changed the pieces because, I had the default chess.com pieces. And so I have my own now. They're kind of garbage because I'm not like an artist or anything. So I had to make them in a sprite. But yeah, I mean, you can tell what pieces they are, so whatever. I also added some sound effects. Yeah. As of now, there is also checks in this game. So as you can see, this pawn is pinned and it cannot move. But you can do this, and I can give you a check, and you can't play any move because you're in check. And so you have to get out of the check, and the only way to do that is to block it with one of these two pieces. So block, and now you're no longer in check. And let's just say I go here. This piece is still pinned, can't move it. So yeah, I also added all of the move calculations, so every single piece should work in this game. So knight works. Let's bring this knight out. The rook. Everything works in this game. So the moves that I have not implemented yet is castling and en passant and pawn promotion. That's it. So you can't castle, which should be easy to add. You can't en passant. So if I do this, well, I guess it's black's turn. So let's just say black. If I could do this, there's no en passant. But that's also not that hard to add. And pawn promotion, super easy. So yeah. So yeah, you just can't promote. But yeah, I got basically all the normal moves down. I haven't made the special ones, and I'll get right into how I made them. So let's go to our chess board, because I actually have not edited the chess window much because it's mainly how the game is actually played. So I have this const car notation which has not been used yet. Okay, so let's just say bool turn just decides whether or not it's black's turn, right? And actually, here, let's go over this. There's a struct for the board. It's basically just a board. That's it. It's just a chess board. I moved it into a struct just to make it easier to program. You'll see in a bit. But you have a vector of boards, which is basically just like a list that you can add however many things you want. And this just shows the history of the game. So at the end of the game, you can get a whole list of moves of how the game was played, and you'll see how I actually use this history in the code later. We have all the movement patterns for all the pieces, which yeah, I'll show you how that works. Okay, so here we are in Clip Studio Paint. Okay, so as for our pawns, let's just draw a pawn. That's a bad pawn. And let's just say like a horse. And we have our king. So all of these guys, they have set absolute moves. The knight can only go left 2, up 1. So all of these guys, their movement is absolute. So all of their moves were pre-programmed in to the thing. So as you can see, it's just a bunch of, if the front of the thing in front of the pawn is empty, then the pawn can move forward. Same with the black pawn and the king as well. If this, and then king as well, if it can move. So yeah, I don't think there's really a way to get around this except for just hard coding it. So yeah, and let's start with the other pieces. Yeah, so let's say this is a rook. Okay, it's gonna be a crappy rook, but yeah, it's a rook. So I basically made a loop. Let's just say this is a white piece right here. Okay, that's a pawn. Uh, and this is gonna be like a black piece over here. Okay, so this is white and this is black. Basically, let's say there's like a square, and then another square, and then the square that the pawn's on, and then a square, and then another square, and then the square that the queen is on. Okay, so basically we have an iterator, which is the offset x and the offset y. And how this works is we're just gonna go offset 1 in each direction to see whether or not you can move there. So this would be offset x plus 1, and this would be another offset x plus 1, and there's nothing there, so you can move there, right? So this is a legal move. So if I give myself green, legal, legal, and once you get to this queen, well, there's a piece there. But since it is a black piece, this is a legal move. But the loop will no longer continue. So let's say there's another square right there. The rook can no longer go there because it has already hit a piece. So let's say for the white piece here, this is legal because there's nothing there. This is legal, but there's a white piece here, and since this rook is white, we cannot move there, right? Because you can't take your own pieces. And so if I add another square back here, let's just say this is not legal because we already hit a piece. And so it's the same with bishops except diagonally. Okay, so let's say there's like a square, 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 and then piece. Okay, this is gonna be a white piece, and then square, 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 piece, black piece. Okay, and we have our offset x, offset y. I forgot to tell you these guys are set to 0. So this would be offset x plus 1, and then all the way up this way, and this would be offset y plus 1, because as you see it's going up. So let's see, 1, 2, 3, 4. So this would be offset x is equal to 4, offset y is equal to 4, and so yeah, it just loops through until it hits a piece. And so we have legal, 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 and then not legal, and that's the same for down here. Legal, 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 because it's a black piece. So I hope you can understand how this works. Sorry about my crappy drawings, but that's basically how moving the chess pieces in a program works. I think that is probably the most efficient way. And so yeah, let's get back to our program. Okay, so we have all these functions that you do to see all the moves of the pieces, right? And we have our pretty much all main function that just loops through the entire board and runs all the legal move calculations and then puts them all into a vector, which is returned at the end of the function, right? So now we have our play move, which basically runs every time you try to play a move, and it returns a bool to see whether or not the move you played is a legal move. So this takes in the move that you want to play. And so, oh, by the way, I don't know if I said this move is a struct somewhere. Chessboard.h. Yeah, move. It just has the old x position of the piece, the old position of the piece, and the new position of the piece. So yeah, that's it. I never defined this. Oh, whatever. Anyways, so it gets every legal move in the current board position, and then it creates a temporary move, right? And so it loops through every single move that is legal, and if the temporary move, okay, so it sets a temporary move equal to the move that we're iterating to, right? And then if the move that we're iterating to is equal to the move that we inputted, then that's the move that we're trying to play, right? So here's a cool part, right? We play the move on the board, and then we get the legal moves of the board we just played on, right? We get the legal moves of the board, And we see if one of the legal moves that the opponent has is to capture your king, then that means that move is check. And so we have to go back in time, I guess, because that move is not legal. Which is how chess works. Because here, let's just get into like a position where I can check the king. If I play any move as black here other than bishop to this square and queen to this square, white can just capture the king. So that's what this checks for. If I have a legal move to capture the king, then I cannot play the move, right? And so that's where our history comes in, because after every single legal move that we play, we add our current board position to our history vector, which was defined here. Wait, here. Yeah, here. Okay, so we just go back in time. You see, equals history assessment. And yeah. Now, if it's not in check, then we add history to the vector. So we push back our board, which means the move was legal, right? And so the history will get like added, and so it, like, if the next move is a check, then it'll go back in time to this position. So that's, I hope that helps you understand kind of how it works. I think that's how it's done on most like chess websites. I see you can scroll back and forth on whatever move. Okay, so future me here, I actually realized that when I filmed this part in the video, I did it completely wrong. So here I am remaking it. This part is going to be correct. So basically what I'm going to be demonstrating for you is a math equation that lets you map your cursor onto a certain chess square so that you actually know which square you clicked on. Okay, so as you can see, we're in our chess program, right? And let's say I click on this square. When I clicked on this square, which is, by the way, square 3 3, because it's 0 1 2 3 0 1 2 3, so square 3 3. When I clicked on this, my mouse cursor was not actually at position 3 3. It's actually at position probably like 500 like comma 700 or some huge number like that. So how do we turn that number into 3 3? Because like that also goes for any other square. So like this square, my mouse was not actually on position 4 0, and etc, etc. So how does that actually work? Well, here we have our pseudo chessboard, right? And let's label all of these sides. So this is kind of like a coordinate grid, right? It's just like that. So we're just kind of projecting a point onto this coordinate grid. Let's say this corner of the board, this is going to be the position of the board. Let's say this is at, we'll make it 50 50. That is not 50 50. 50 50. And let's say we clicked right here, and I have to be a little precise. So let's say this position is 380 by 480. That is the position of our mouse. And this board is 800 by 800 pixels, right? So how can we tell which square this point is on? Well, we can already tell using our eyes. It's on point 3 and 4. But how can we tell in a program? I mean, our program doesn't have eyes. Well, there's a math operation that we can do. Okay, so step 1, we need to find the relative position of this point to the position of the board. If we're assuming that the position of the board is mapped at the top left corner. So in this case, it would be 380 minus 50, comma 480 minus 50. So step 1, relative position, 380 minus 50, comma 480 minus 50, which gives us 330 comma 430. This is why math is important if you're a programmer. Now, okay, so now that we have the relative position, we need to find sort of an iterator that gets us from one pixel or one square to the next square. So we have 8 squares and our board is 800 wide and 800 tall, so that means every single square should be 100 by 100. And the way we find that, we find the iterator, that is 20. We find the iterator is the size of the board, which is 800, divided by the number of squares on the board, or the to make this more applicable to other programs, the number of pixels. How would you say it? Like nodes, cells, I don't know. Which is in our case 8. So the iterator is 100. So what we're actually doing here is we're finding how many 100s can go into this point. So 1, 2, like we see 1, 2, 3, 300. 1, 2, 3, 4, 400, right? So how can we do that? Well, 3, we take the relative position, so let's just say for x it's 330, and then we find the remainder of this x position divided by the iterator. So, which was okay. So that's what the modulus operator does. So the remainder of 330 divided by 100 is equal to 30. So then we subtract this 30 from our 300 to make the 300 divisible by our iterator. So which is equal to, okay, so 330 minus 30 is equal to 300. So now that our x position is divisible by 100, we just divide it by 100. So 300 over 100 is equal to 3. And as you can see, that is the square that we're on our x position. So 3, right? Square number 3. We do the same for the y. So we have our answer, which is 3, 4. Which, as you can see, 3, 4. That's the position of the board that we're at. Because in programming, we always start from 0. Okay, so we're going to put this all into a nice equation that will solve this for us. And to do that, first we need to set like kind of variables, okay? So we're going to have x, y, position of cursor, and then px, py, position of top left of board, sx, sy is equal to size of the board. So that's going to be like our variables, right? So well, first of all, we need to write out step 1, which is finding the relative position of our cursor to the board. And the way we do that is the position of our cursor minus the position of the board. That gives us our relative position, as you can see right here, 380 minus 50, our board position is at 50. And then, step 2, we find the iterator, the size of the board, so sx divided by the number of tiles, or squares, which is 8. That is the iterator, right? So now that we found both of those, what do? We get the mod, or the remainder of the relative position divided by the iterator. So that would be this. And then we subtract the remainder from our relative position. So this would be x minus position of the board minus this. And we can put this in parentheses if you want to. That gives us a number that is divisible by the iterator that also shows us what tile our cursor's on. So now all we have to do is divide this number that is now divisible by the iterator by the iterator. So if we put all this in parentheses and then divide it by the size of the board divided by the number of tiles. So that is the equation for finding the tile that our cursor is on our chessboard. And we just kind of also just run the same thing for our y. So if I replace this all with y, you can see that gives us the mapped position of our y coordinate. And so if we look into our program, it's right here. I implemented this exact equation. If I zoom in and make this less ugly, I implemented that exact equation right there. It's pretty useful, like if you have kind of just like a whole array of tiles that you need to map your cursor to. Like if you have an inventory, I'm sure that's probably how they did like Minecraft inventory, where it's like a grid of tiles, and you know, all sorts of stuff. So this is pretty important mathematical operation. I guess we could even put like a variable, another one, which is just like t is equal to number of tiles in that direction. We could put like tx, ty. We can replace this with tx and ty. So pretty useful mathematical operation. Probably not too useful on like a game engine, because they probably already have like buttons. If you're making a game from scratch, this is pretty useful. That I found I use this equation a lot. So yeah, that's my fixed version of this math equation. I wasted 20 minutes on this on the old recording, and I got the equation wrong because I'm dumb, but I got it right this time. So hope you learned something. Math is important. And back to old me doing the outro. So that's pretty much all I did this episode, or this week. So thanks for watching. Next week my plans are adding the special moves and making a menu screen, because I don't want this just to be chess. I want there to be like a chessboard editor, like you can 1v1 engine, you can review your games, you can input games. I want to add a whole bunch of features to this. So yeah, next week, menu, special moves. That's my goal. And yeah, okay, see you guys in the next video.